we want to find a vector that is orthogonal to the plane by these vectors. We have three of them, A, B, C, and three vectors can't form a plane, four of them can. It depends on the scenario. I mean, one of them could form a plane. Know that from 12.1. In 3 dimensions, when I say x is equal to 2, I'm not referring to a line. I'm referring to one dimension less than the, sorry, if I said 2, 2, 0, I'm referring to a plane and I'm varying all kinds of, varying values for z. And same if x is equal to 2 and so forth. Let's see. 3, 1, 1. So I'll put somewhere over here. 5, 2, 4. Yes. Way down here, 8. Down. 5. This would work. Okay, and 3. Somewhere there. Good. And now I want to find a vector that is orthogonal to the plane. Naturally, you might be wondering, what the hell? There is no plane. Do you see a plane? Kind of. Chase why?
I just feel like there's going to be one if you made a plane between the 3 points instead.
Between the 3 points, that's the key. Plane formed by the vectors, or the plane that passes through, and that's what I will have. Yes. So that is A, B, C. That shaded part is the plane. It's probably somewhere like this. I just can't draw them. Now, again, I picked something directly from the text because if I picked something arbitrary, I wouldn't be able to draw this plane. Okay, I want to know something or a vector that is perpendicular to the plane that's formed by these 3 vectors. We have the plane, we want to find the vector that is perpendicular to that plane. How do we find that? So orthogonal means perpendicular to this plane, correct? Mm-hmm. And easier way is, passing through one of the points. Agree? So I can form an orthogonal vector right here. Agreed? Do you agree that that vector is orthogonal to the plane? Yes or no? Why not?
It's only orthogonal to the point.
Come again?
It's only orthogonal to the point.
It's only orthogonal to the point. If I move this over here, is it still orthogonal? How about over there?
Yeah.
Orthogonal to
C point, yeah.
How about there?
To be,
Come again?
yeah.
It'll be orthogonal to that. if I move along the diagonal, for instance, if I use what law, go from a triangle to a parallelogram, what is that law?
Grant.
You can put the arrows if you want. So the plane is somewhere over here. If I move this A along the diagonal, will it still be orthogonal to that plane? That's my question. Do you have a sheet of paper? Oh. How do we find the cross product? What? Determinant of a matrix, the first row is ijk, and then you put the two vectors. Now, I want to know that makes up. Yes, from here to there. What is that vector? Is it just 5, 2, 4? No.
Would you subtract A from B to get 2, 1, 3?
Will I? Should I? Must I?
Makes sense to me.
So I have to subtract, correct? So that will give me the vector, because if I started at the origin, not a big deal. But what we know about vectors is from origin to this point right here is no different from that. Good. See, now you know the effects of my trip down the hall. There, here, you know, got a joke. You got the joke. So, not really, that was just a joke. So, we have to account for the shift from origin. So first we can find the AB vector from A to B, 5 minus 3, 2 minus 1, 4 minus 1. Now one may say, well, what if I accidentally did B to A? Would that be a huge mistake?
The
Sign would just be different.
It'll just be the opposite, right? What we know about orthogonal vectors is they can change in sign. One can go this way, other can go that way. Not a big deal. Then B to C. So 8, 5, 3. This C. So 8 minus 5, 5 minus 2, 3 minus 4. There, 2, 1, 3, 3, 3, -1. Yes, if I find the cross product of those two, I'm going to get a vector that is orthogonal to those two vectors. So cross product of AB, BC. What do we get? You can do this good practice. Let's find the cross product of those two. We already did a problem on parallelepiped, finding the volume, correct? Scalar triple product. Okay,
Yes.
so properties, we've got one. One more time. Okay, do we have the cross product? So once you find the cross product, I want to know if it is in fact orthogonal. Yes, how do we verify that?
Could we do a dot that cross product equals to
A dot the cross product, or B dot the cross product, whichever one. So let's find the cross product first. IJK, again, determinant notation, I'll simply put IJK, first vector, 2, 1, 3, second vector, 3, 3, minus 1. Again, it doesn't matter if you swap them in this case, not a big deal, we'll just give you another vector. I vector, first element or first row, that is your submatrix, 1 times minus 1, minus 3 times 3. Next, J vector. Is it just J vector or minus J vector? Minus J. Which would mean we ignore this column, pick those two, 2 times negative 1 minus 3 times 3. Lastly, K vector. Pick those two, 2 times 3 minus 3 times 1. Good, yes. Now, I vector multiplied by negative 1, negative 9, that's negative 10, minus J vector, minus 2, minus 9, minus 11, K vector, 6 minus 3, I get 3. So negative 10 I vector plus 11 J vector plus 3 K vector. Good, okay. Now we can determine if something is orthogonal or if a vector is orthogonal to another vector, we simply take the dot product, yes. If you have to pick one, which vector would you pick to test, hypothetically speaking? Probably B. So this is what I want you to do. I want you to find A dot B, A dot, I'll call it M vector, A dot M vector, B dot N vector, C dot N vector. Tell me what you get. Should be easy. Okay, so do make that correction. Get rid of that magnitude part. It was silly. We need to have a vector. If you want, you can put vector notation here. I forget it occasionally because, you know, I'm starting to push it off. Put arrows. That's beneath. They are beneath. Moving on. So, what did we get for A vector dot N vector? Huh? 0. Did we get 0? So negative 10 times negative 3. Yes. Plus 11 times 1. 3 times 1. Why are you shaking your head?
because that's not 0.
Okay, so Jay, why is it not 0?
Oh, I thought we were doing a dot AB.
Okay, so AB, why AB?
Oh, let's do it.
Oh, you mean at B? Are you referring to B dot N?
I was doing AB dot N, because
Ah.
AB is on the plane, and then that's perpendicular.
My bad. Yeah, you're right. Can't do A dot N, but if you did A dot N, you would get negative 30 plus 11, negative 19 plus 3, negative 16. B dot N, 5 times negative 10, 2 times 11, 4 times 3. And that is going to give me negative 50, positive 22, negative 28, positive 12, negative 16. Yes? And lastly, this one, A times negative 10 plus 5 times 11 plus 3 times 3. Negative 80 plus 55. Negative 25 plus 9, negative 16. That's interesting. Why are we getting negative 16, negative 16, negative 16? When we find the dot product between two vectors, we are going to get a scalar. But what does dot product give?
Magnitude of a resultant vector.
Another way. Ellie,
Are they all 16 because this orthogonal point is in between the plane itself? So it's the same distance from each point?
exactly. So, absolute value is 16, Haley got that part right. Now, still didn't answer the question, which is when you do the dot product of two vectors, what do we get?
A length.
The length of the vector that you have. Now, if it is from 0 to 5 to 4, you just square each of them, you get the length, yes? Now here, I'm getting 16, and this B that we chose is common to both A and C. So whatever vector that you have is going to be equidistant, right? Again, doing parallelogram lower downward. Now that I've given you the hint, but I drew it that way for a reason. You can see the arrow, that would explain the negative part. So what does the negative tell us?
Going down. Going down.
It's going down, right? It's going this way. That were to be positive, it's going to go that way. Well, does it matter? Or doesn't? Because we know from last time, if you have a vector that is orthogonal, every scalar product of that vector is also orthogonal, correct? So this could be negative of this one. You can have this, stretch it, stretch it, stretch it, doesn't matter. Still orthogonal, do we agree? Going straight on. Okay, now let's find the dot product of AB dot n vector BC dot or BC vector dot n vector. Dot product between those two, tell me what you get. So dot product of AB vector, n vector, negative 20, negative 10 times 2, negative 20, 11 times 1, 11, 3 times 3, 9, negative 20, positive 20, 0, BC vector dot n vector, 3 times negative 10, I get negative 30, 3 times 11, 33, negative 1 times 3, negative 3, and 0 again. Yes, so the vector AB is perpendicular or orthogonal to n vector, correct? Kyle, did I change your mind? Okay, now if I move this along this line, move this vector along that line, would it still be orthogonal? Yes. Reason being, whatever vector that you place here is simply a scalar multiple of the vector B. Okay, so scalar multiple would mean the vectors are pointing in the same direction. Magnitude is the only thing that's going to change. If I move to a different point, let's say I moved it over here. Hypothetically, should I repeat the process?
The whole figure is.
No, just the vector. In other words, if I have to find that. But if you have to find that vector, what will you do? You would do BC vector, yes, times AC vector. Correct. Give it a try and tell me what.
Would it be AC or would it be CA vector?
Doesn't matter.
Doesn't matter.
Yeah. Because it's only going to differ by side. If it's going to make you happy, we'll do it CA. Right? I like California, so we'll keep it that way.
Oh man, I want AC again.
You don't like California? Such a
Well, yeah, we're going, you know,
California.
Okay. We moved from AB vector times BC vector. We already know the BC vector from last time. 8 minus 5, 3, 5 minus 2, 3, 3 minus 4, negative 1. CA vector. 8 minus 3, 5, 5 minus 1, 4, 3 minus 1, 2. Good. Now we have to cross. So BC vector cross CA vector. I, J, K, 3, 3 minus 1, 5, 4, 2. I'm calling this M vector. So I vector times 3 times 2, 6, minus 4 times minus 1 will give you 10. Negative J vector, it's a common mistake. So do practice. Very common mistake when you first do the tandem. So negative J vector, ignore those two. 6 minus of minus 5, 11. K vector, 12 minus 15 minus 3. Which would give me 10. I vector minus 11 J vector minus 3 K vector. Now you would understand as to why I started with AC vector and J ruined my game. Right, and I went with AC vector, this would have been.
Wait, isn't it the other way around?
What do you mean?
If you did A minus C, wouldn't you have gotten?
A negative. So it'll make this one equal to the previous one that we had. What is n vector? Negative 10 plus 11J plus 3K, right? Okay.
No, wait,
Yeah, but
I think what he's saying, if you found CA vector, you would get
The same one.
-5.
No, if I did AC vector.
Wait, what?
No, I think you did AC vector. AC is 5, 4, 2. I think CA is -5, -4, -2. Yeah. That's what I
Yeah,
did.
because I did.
Oh, did I have it backwards? Okay.
Try to no, me, man, that's.
C is X3, Y3, Z3. X1, X2, or Y1 and Z1 is minus that direction is this way.
It's
CA.
Isn't it, if you do CA vector, isn't it A minus C?
Yeah.
It's from C to A.
Because
No,
DC vector.
oh, I
is minus
see,
B.
I see, you're choosing the town, excuse me, initial side to be here, okay. Fine, so,
Doesn't it have to be consistent?
come again?
Doesn't it have to be consistent? Like, cause you did C
Yeah.
minus B, wouldn't you have to do A minus C?
It has to be consistent, but in this problem, it doesn't matter.
Okay.
Okay, so the point I'm trying to illustrate is the vector that we had, M vector, was -10I vector. Positive 11J vector. Positive 3K vector, yes? And that one gave us this. Agree? What is that one giving?
Same thing.
If you did A dot M, what would you get?
It would go up from C.
We'll just do A dot M and then we can just believe. 3 times 10, 30. Plus 1 minus 11, negative 11. 1 times minus 3, minus 3. Positive 16, yes. That one was negative 16, this one positive 16. The length is the same, what changed?
Magnitude.
Direction.
Direction, I mean,
Direction.
well, I said the magnitude. I meant
So-
the magnitude.
Ah.
It's like by scale.
Yes, it's just pointing in the other direction. Now, Rachel asked, well, should it be consistent? Well, if you switch AC, CA, doesn't matter in this problem, because when you switch and do the subtraction in a different way, instead of finding that, you would find it. That is all. Good. Now, if I pick an arbitrary point, let's say centroid of that plane, right in the middle, would it, if you compute a vector orthogonal to that plane, will you get the same answer? Yes, you will get the same answer. That is the central. So if you draw a vector there, it should be parallel to that vector. So corner points, good enough. So that would answer your question from earlier also. Would it matter? No. Now that you know how to find whether I find a vector here, there, or there.
In physics, would that mean you could
In-
find the center of mass that way?
Yes, centroid is the center of mass. So going back to the question, would it matter, Chris? Which point, so when we first started, you asked me a question, right? What do you think now? Would it matter?
I don't think, no.
No, it doesn't. And sheet of paper, good example. Good. Now, if I want to find the area of that shaded region, in other words, area of the triangle formed by those three vectors, will it be, well, how would we find it? First, should we get a vector as an answer? No, area is a scalar, great. How do we find that area?
I find the angle between two of the vectors.
Angle between, okay,
That's the first, the reason I'm thinking about that is because last class, what formula was it? It was the cross product of the magnitude of the cross product of two vectors
mhm,
is the same. Like the structure of the formula is the same thing as the area of a triangle in terms of trig.
area of the triangle or area of the parallelogram?
Or no, yeah, parallelogram, but
Parallelogram,
by two,
okay.
yeah, parallelogram.
So Chris actually said, started with an angle, but then later he goes, oh, last time the magnitude of cross product is simply the area of the triangle corrected to area of parallelogram, right? That's it. You corrected yourself. Do I need the angle? Is it necessary?
No.
No, because I have the cross product already. So if I find its magnitude, I'm going to get the area of the parallelogram. Does it matter which one you pick?
No.
No, because the magnitude will be the same, even though in my picture, they don't look the same because I don't want to cross over there. In our case, it's square root of 100 plus 121 plus 3
Plus 9.
Oh, that much, plus 9. 130, 230. You can simplify if you want, but that's not divisible by 4. It's divisible by 2, not divisible by 3 or 9. So that's the best I can do. That's it. Are we done?
No,
No, why not?
because that's the area of the parallelogram. We wanted the area of the plane, which is a triangle. So
Yeah,
we just
well done. We wanted to find the area of the triangle. We ended up with the area of a parallelogram. What should we do?
divide by 2.
Simply divide by 2, because the parallelogram is an extension, excuse me, parallelogram law is an extension of the triangle law, you know, go this way. So if you find the surface area of this plane divided by 2, you'll get the area of the triangle. So the area of the triangle, desired triangle, is simply half of square root of 30. Let's write it here. Before I go to the next problem, if I move these 3 points in the same direction, say up, will I get the same area? Yes. But if I fix A and B, pulled C this way, will I get the same area? No. Now do you see why direction matters?